Hello students, in that last video we talked about the definition of an angle in trigonometry, and it basically expanded the idea of an angle from geometry, where we now have an angle that could be anything between negative infinity and positive infinity. And again, the goal of this is what's sort of written here, alluded to in the lesson, is trig ratios of any angle. Positive, negative angles, very large angles above 360 degrees, anything like that at all, we can find a trig ratio for. And we're not quite ready to do that yet because we need to explain what's called a reference triangle. So I'll draw this picture first. So let's say I have a point here. I have, a side here that's been rotated all the way over here, some amount of theta. And so this is the side now. In order to do something with a trig ratio, I really need to find a triangle, in fact, a right triangle in order to make this work. So the way I can do this is by extending a line down here. And now this triangle right here is a triangle where I can use to find some trig ratios. Okay? And so to explain and define this term reference triangle, it is a right triangle formed by connecting the terminal side to the x-axis. And I'm going to underline x-axis here because it's not really necessary that we do this. We can do this with the y-axis as well, but it's probably less work, and in most cases I would say using a reference triangle to the x-axis is more convenient than doing that to the y-axis. Okay? And one of the things that's a little bit weird here, and you'll see this soon in a minute, is that we're gonna get trig ratios of this angle theta, even though theta is an obtuse angle, even if theta is negative. And in this case, if you notice, theta isn't even in the triangle, but we can still find the trig ratio for that using the triangle to help us. So let's look now at the definition of some trigonometric ratios. And before we do that, let's define a few other terms here. So we're going to say for a point P with coordinates x, y on the terminal side of an angle, and we're also going to say let r be the distance of xy, or P, to the origin. And if r is the distance, then, and I'll draw the picture on the side here. So let's say P is, we'll use this triangle again. It's been rotated this much. This is angle theta. This is the side. This here is x, y. Okay. We can say that r has to be square root of x squared plus y squared. And this is just the distance formula. The distance from this point to this point, we can do that using the distance formula or the Pythagorean theorem. We can extend this down here and we can make our reference triangle. So now we have defined a point P on the terminal side with the coordinates and with the distance to 0, and this means that r is always positive. R is always positive, okay, because it's a distance. We can now talk about our trig ratios. So first we'll start with the sine ratio. Sine of theta is defined as the y coordinate divided by the radius. And if you look at this picture here, if this is theta, the angle that's sort of opposite of that, or the side that's opposite of that, is this side right here, which has a length of y. And the side that's adjacent to that is this side right here, which is x. Okay, the same thing as the x value. So when we think about this, there is somewhat of a loose relationship between the circle, an angle in standard form from trigonometry and an angle in geometry. There is y is sort of the opposite side, r is the adjacent side. You can also see that cosine of theta is the adjacent side divided by the hypotenuse, or in this case r. Let me label this as r. So it's x over r. And then tangent, what we're used to seeing is opposite over adjacent, but it's now y over r. I'm sorry, y over x, as long as x is not equal to 0. Cosecant of theta is the reciprocal of sine, so that's r over y, as long as y is not 0. Secant of theta is r over x, as long as x is not 0. And finally, cotangent of theta is defined as x over y, once again, as long as y is not equal to 0. And we'll talk about what happens in terms of these ratios when y is 0, and if that's even possible to have trig ratios at all. But I want to point out that this is a new way, a shift in our thinking about angles and trigonometric ratios. In geometry, we're so used to saying opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. But now we have some new definitions here. And it's not all that new, it's just more general, where sine is, instead of opposite over hypotenuse, it's the y value divided by the radius. Okay? And one of the things that we need to note in this scenario is that trig ratios now may be negative. Trig ratios, okay, may be 0 or negative. Okay? Whereas before all the ratios were some positive number, now in this new, more general way of looking at trig, the ratios may be 0 or they may even be negative. And I'll explain what that means with the next couple of examples. So we have a few examples here that say that P is on the terminal side of angle theta. Evaluate all 6 trig functions, or 6 trig ratios for theta. The first one has us doing P is at the coordinates of 4, 7. So go over 4, approximately up 7. This is P, 4, 7. And we can kind of draw the triangle in here so we can have a visualization of what's happening here. And it's been rotated, theta degrees or theta radian. We actually don't know what theta is measured in at this particular point. So one of the things we should always do is try to help ourselves figure out the values here. So the length here along this triangle is 4. This length here, that's the vertical length, that's 7. And let's find r. R is right here. And we can use the Pythagorean theorem. R is 4 squared plus 7 squared, square root of the whole thing, which is 16 plus 49, that's 65. So square root of 65. This cannot be reduced any further. And so now we know that this is x, this is y, and this is r. We can fairly quickly get all of the ratios. And when you're learning this lesson, you should really try to think about all of these ratios in terms of x, y, and r, and try to steer yourself away a little bit from thinking too much about opposite, adjacent, and hypotenuse, because that works sometimes in this new world, but not all of the time. So let's look at cosine. Let's start with sine. Sine of theta is, by definition, y over r, so this is 7 over square root of 65. If we rationalize that, we get 7 square root of 65 over 65. Let's keep going. Cosine of theta is, by definition, x over r, which is 4 over square root of 65. And when we rationalize the denominator, we get 4 square root of 65 over 65. Tangent of theta is y over x, so that's 7/4. And that was straightforward enough. You can also look at the other 3 ratios. Let's see. Let's go with cosecant of theta. This is r over y, which is just the reciprocal of sine, so that's square root of 65 over 7. Secant of theta is r over x, and this is square root of 65 over 4. And finally, cotangent of theta is x over y, which is 4 over 7. So you see we have 6 trig ratios defined using the definitions of ratios that involve x, y, and r, and everything still works. And if you notice here, this point here is in the first quadrant, so it behaves just like any acute angle. Theta is an acute angle. So in the first quadrant, theta is acute. So that's one of the things we can note here. In Q1, theta is acute. And when theta is acute, it behaves very similar to the examples with triangles. Now let's try another one, another example. This time, P is negative 4, 2. Okay? So if I draw my picture out here, I get negative 4, 2. That's approximately here. Negative 4, 2. Sort of shade in this reference triangle a little bit here. And let's find r, because r always helps us. So this is negative 4 squared plus 2 squared. This gives us square root of 20, which can be reduced and simplified to 2 square root of 5. So this is going to be very helpful to us. And now let's look at our trig ratios. So let's start with sine, which is, again, let me move this a little bit to the left here so I have enough room. Sine of theta is equal to y over r, which gives me 2 over 2 square root of 5. And if I cancel those two, I get 1 over square root of 5. And once you rationalize the denominator, you get square root of 5 over 5. That's sine. For cosine, you have x over r, and this is where things get a little bit interesting. You have negative 4 over square root of 5. Okay, let's rationalize that denominator, and you get negative 4 over 2 square root of 5. So this gives me negative 2 over square root of 5, and that will be rationalized to negative 2 square root of 5 over 5. And one thing we notice here is that the trig ratio is now negative. The ratio is a negative number, okay, which is not something that happens at all in our our geometry classes. Okay. Let's do tangent of theta, which is y over x, 2 over negative 4, and this gives us negative 1/2. Now I'm just going to continue doing this work and building on these concepts. I'm going to go on forward with cosecant of theta, which is r over y, and this gives us what we had here before. This is 2 square root of 5 over 2, which simplifies to square root of 5. I need secant of theta, which is r divided by x. R over x, that gives us 2 square root of 5 over negative 4, which then simplifies to square root of 5 over 2, negative square root of 5 over 2, I should say, because that's the correct answer, negative 5 square root of 2. And finally, cotangent is x over y. X is negative 4, y is 2, and this gives us negative 2 as our final answer. And once again, I want to point out that these definitions of trigonometric ratios are expressed in terms of the coordinates x, y, and only one distance, which is r, which is a different definition and slightly different concepts than what we've worked on before using triangles. And all this really means is that it matters about the orientation or the placement of our triangle. If we didn't have an xy coordinate plane, all of these numbers would be positive. But because we have an xy coordinate plane, we have to make sure that we use negative numbers where they are defined, when they are appropriate. Now let's look at one more example here where we have an unusual case of cosine and sine theta being either 0 or undefined. Okay, we have one final example, part to example 2, which is when point P is 0, 6. So there's my xy plane. By estimation, 0, 6 is approximately here. And we can do what we did last time by finding r, which is square root of 0 squared plus 6 squared, which comes out to just 6. So one thing that's a little bit weird is 6 and y are the same thing. I'm sorry, this is r right here, right? And this is y, this is x. R and y are the same thing. I'm going to erase this so it doesn't look like 6 over r. Sorry. But this is y, this is r, and they're the same thing. Also, x is 0, and try and draw a reference triangle for this, and you'll find quickly that you really can't. Okay, so there's no reference triangle in this case. No reference triangle, because you're supposed to connect this somehow to the x-axis. Okay, but if you just draw a line straight down or straight left, it's not going to work. But we can still define cosine, sine, and theta. So cosine, once again, is x over r. X is 0 over 6, that's 0. Sine of theta, 6, y over r, so that's 6 over 6, that's 1. Box these answers here. Tangent of theta is equal to y over x, which is 6 over 0, and that is undefined. Okay, so this is a new result here that we have not seen before, because you have no reference triangle and you have some ratios that are 0, 1, or undefined. Let's continue here. Secant of theta is r over x. In this case, which it is 6 over 0, and this is also undefined. Cosecant of theta, or the reciprocal of sine, is, well, r over y. R is 6, y is 6, the ratio is 1. Finally, cotangent of theta is x over y. X is 0, y is 6, cotangent is 0. So in this case, every single trigonometric ratio, is either 0, 1, or undefined. Okay? And this is a special case of what's called a quadrantal angle. Define this here. This is called a quadrantal angles, or angle. And this is an angle whose terminal side is on one of the axes. So it's either at this point here, some point on the x-axis, some point on the other side of the x-axis, or some point on the negative side of the y-axis. So angle whose terminal side is on the axis. And the measure of these angles is either 0, 90, 180, 270, 360, 450, and so on. So the measure of these angles, 0, 90, 270, 360, and onwards forever. And one thing we can say is, to shorten this up, is that it's multiples of 90 degrees. Okay, so a quadrantal angle has these weird, unique qualities, and the measure is always a multiple of 90 degrees. Or if you are measured in radian, it's 0 radian, pi over 2, 3 pi over 2, 2 pi. And that's just another way of saying multiples of pi over 2. And there you have it, a continuation and some examples of dealing with angles and trig ratios in trigonometry. We have some new situations here that could be different. We have some examples where the new trig ratios are the same as the old ones, some where they're a little bit different. In other words, they have a negative or a minus or a positive in there. Now we just have whereas before everything had to be a positive number. So I'll end this video here. This is a fairly in-depth, long lesson, so we're going to do this over multiple videos. I'm going to continue on the next one, which talks about periodic functions.